Good morning to everyone. I'm happy to know that the previous student is researching on the same line as I do. I'm not alone. So I'm going to talk to you about C++ contracts, which is more or less the same idea that you have seen with the previous student, but this is going to be on the standard, hopefully, for C++20. First of all, I have been already introduced at the very beginning of the students' research competition, but just in case you want to talk to me during the poster session, just for you to know a little bit more about me. I have been working just like hacking some code for the Linux kernel. I also like working on my own embedded systems, microcontrollers and those kind of things. And I'm also interested on electronics and almost everything that is low level. And in the last year, as part of my PhD, I have been hacking on the Clang code base. So let's start with an introduction. Right now, we have in C++ 17, we have the static assert thing, which is only for compile time checks. And we have the good old C assert macro. But this is kind of limited. This is aged by now and might be improved by today's standards. We are expecting to provide much more information to the compiler than we can do right now using the assert macro. This is going to be a spoiler of what you are going to see. Somehow, if it gets finally approved, it's currently on the, this is reality, I mean, it's currently on the working draft for C++20. So this might be real if it's finally approved for the final standard next year, hopefully. So this is kind of a spoiler. We can have preconditions, which are annotated with the specs attribute, postconditions for functions that are annotated by the ensures attribute, and we can also have, although not shown here, but we will talk about later, we could also have assertions in a specific point of a function. And then this could go on a header file, and then your implementation could be written in the usual way. So we can go lunch. This is almost half of the talk. Now, talking seriously. This is, I'm going to make some introduction about the, because I'm guessing that nobody is familiarized with this because it's kind of new. It's going to be introduced in the next version of the C++ standard. And this is the official proposal, the P05 blah, blah, blah. This is the official document in which the C++ committee maintains this proposal. And this is a proposal, as I told you, to introduce C++ contracts. What is a contract? It's a set of preconditions, postconditions, and assertions which can be specified as part of a function. A precondition is what the function expects to be met at the entry point of the function, and is annotated, as I told you, with the specs clause. Postconditions are expectations at the end of the function, so before returning from that function, and are annotated using the ensures attribute. And assertions. Do I need to find this? No, seriously. These are annotations that you can use at any point of your function body, much like you use the assert macro. Also, any of these three attributes can contain an assertion level which specifies the relative cost of the computation. So when you are building the translation unit, it will take into account up to a given level. So you can emit some checks or ignore others. Currently, we have three levels. One is the axiom level, which is used for checks that are not evaluated at runtime. This is useful for static analysis tools or for hinting the optimizer, that you are just like telling the optimizer that this condition, this predicate is going to be true at that point. So the optimizer can act upon that condition. And the default and audit levels, which are intended to be used depending on the relative cost of the computation. So you could put audit if it's a highly costly check, or default if it's not. Also, a translation is carried out with a given build level. So you can, we have currently now 3 levels, which are off, default, and audit. Off turns off all checks. Default takes into account only default checks, and audit takes into account both default and audit checks. Don't worry about that. We are going to see an example later. Also, for the ensures attribute, we are accepting another identifier, which should be placed right there, which can be used as part of the predicate and will refer to the actual return value of the function. So you can place x there and say x greater than 0, for example, and you will be referring to the return value of the function. What happens when you violate a contract? Say you have written a precondition and it is not met at a given point. By default, the emitted code will invoke the std terminate function. But you can also specify a customized handler. This is to be used for easing the transition to contracts. So if you don't know if your contract is actually failing or not in a production environment, you can annotate contracts, and the interim, before enforcing them, you can be logging violations. So you can just define your own function which logs to the std error or something. You can do whatever you want. You can even throw an exception or whatever you want. Your violation handler shall be passed an object, a reference to an object, which is of this type, contract violation, and these are the members. So whenever your violation handler is called, you can access the line number, the function that the violation occurred on, the line number, the level of the contract, and so on. This is all in the previous document, in the P054. You can check it out on the web. So to sum up, a contract should have no observable effect on a correct program. It should run the same. It shouldn't change its behavior, besides a performance penalty. And it might be a convenient way to specify additional information to the compiler or third-party utilities. So I did an implementation of this specification, of this technical specification in Clang. I'm not going to tell you all the intricacies of this because it's going to take so long. But I did changes to almost all the components of Clang. I did changes to the parser because if you take a look here, you will see that this is not the standard attribute spelling for C++11 attributes because there is a colon there. So I just I added some grammar rules proposed by the technical specification. I also changed this semantic analysis component. Most of the code of my implementation lies there, such as declaration injection for the user-provided handler and so on. The merging of attributes between compatible redeclarations, and instantiation in case that predicates are part or do have identifiers that are dependent, that are part of a template. I also did some small changes to the AST context and function decal classes, just to store some additional information I need to keep around. And the code gen, of course, just to generate the code for the checks at runtime. I'm going to just enter in a little bit of detail in how functions that are annotated with preconditions or postcondition are generated, their code are emitted. So, fine. The thing that we are doing here is whenever we are emitting a function that is annotated with preconditions or postconditions, we are going to clone that function decal. We are going to split it into two, the checked and unchecked version. So the unchecked version will preserve the original code of the user, and the clone function is the one who is going to preserve the original code of the function, as you see in this diagram. And the original function of the user is going to contain synthesized code to check the preconditions, make a call to the unchecked function, and then check for postconditions. The important thing here is that the unchecked function is marked as always inline. So it's going to be inline as part of the check function, as you will see later. So there is no penalty on this. There is no additional function call here. So this is an example of how this works. You can see a function f, which is annotated on a header with a precondition. And you can see the actual implementation here. It's a simple function, but you can write complex things. It works. So this is the actual IR generated code. You will see that here it is checking the predicate, and it will branch to here if it does not meet at that given point. And it will branch otherwise to the return statement if the precondition is met. So you see here, as I told you, that there is no additional function call to the unchecked version of that function because it is being inlined as part of the checked version. So the C++ ISO committee noticed that there were some problems, just in case you were compiling your translation unit with some checks disabled. But if you assume all checks or all preconditions or postconditions that the user has specified as always true, you will be facing some problems, like some of the lower level conditions being optimized out by the optimizer. So say you have an an audit condition that checks for a pointer not being null, but you are compiling you are actually translating your translation unit with a level of default. So if you take all preconditions as true every time, any other precondition of a level of default will be optimized out if it takes into account the other condition, the null pointer assumption. So what did we do here? The current proposal of the C++ committee is just not to assume any condition that is not being checked. So you should only assume, if you are compiling up to the default level, you should assume only up to that level. If you are compiling up to the audit level, you should assume all conditions. Additionally, conditions specified as axiom, because they are axiomatic, should be taken for granted. So they should be assumed always. There is also a proposal to ignore, to optionally ignore some the axiom conditions if you put like axiom mode equals off. So we evaluated this with annotating the basic string class of the GNU standard library, and we replaced their macros the assertion macros with our contracts, and this is what we got. We got, when using the square brackets operator, we got almost somewhere from 5 to 10% of improvement in runtime. And for something which is compute bound, we get almost the same. So there is no penalty on using it. You can try this out. We have a compiler explorer instance running. So I don't know if you are able to see it. You can try this on your own computer if you want. Just use that URL. Well, you can see it anyway. So let's see what happens. I'm going to erase all this and put something simpler. Like int, for example, AB. I'm forgetting the type here. So this is really simple. But you can try it on your own computers if you want to try more complex code. So we are going to say that this expects that A is greater than B. And you will see that the compiler is generating code for it. You can also play with the options. I'm taking here into account up to the audit level. And I'm also using a custom handler that could be defined in other translation unit. Just in case you are interested in testing this, because you cannot see the URL right there, I'm going to show you here, which is much bigger. So you can try it on your own computers. The actual implementation has been open sourced, so you can take a look at it. And it's going to be rebased on top of the current development branch of Clang, which this fork is kind of old, and I'm going to update it. And I'm going to submit it as well to the LLVM code review. But that's not all. We have made something with this, actually. I'm going to be really fast. We tried to annotate some conditions to improve the threat sanitizer detection. So we actually had some data structure, which is log-free. In fact, it was the push log-free SPSC queue with only one producer and one consumer. And we tried to extend the threat sanitizer to support some user-defined semantics. So this is how it goes. You can express predicates like having event sets. Having event sets. And then you can compare a pure happens before relationship between all the events that are on this set and the current event. So you can, well, take a look at this, and we will discuss it later on the poster session if you want, or just here. So it will give you, hopefully, some more descriptive trace of what is happening. In this case, we are violating the semantics of the SPSC queue because there is two concurrent producers. And this is also open source. It is currently maintained as a branch on the same repository. You can also take a look at it and just try it out and let me know if it works for you. And as a conclusion, contracts helps to detect more programming errors, and this boils down to improved correctness of software. Runtime checking can be disabled or enabled, which is the trade-off between safety, software safety, and runtime overhead. The question, can I throw, instead of aborting the program, can I throw an exception or log violations? Yes, you can. Use a custom violation handler and you're done. And this is a portable and standard way of providing additional information to the compiler or part of the compiler, such as the optimizer or third-party utilities. Additionally, few issues remains to be fixed, just 3 of them. So if you want to contribute, you are welcome as well. So thank you for listening. And time for questions. questions time.
Got a question. You talked about the interaction between contracts and optimization, but you talked about it one way, which is assuming what is in the contract to optimize the rest of the code. And with the way you implemented it, can it have another impact in the other direction? Like the code will remove some checks. For example, if you have a check that a pointer is not null, and then inside of the function you dereference the pointer. Since you dereference the pointer, the optimizer.
Can you start over again the question? Because
okay, let's go directly to
I wasn't listening to the first part.
Okay, let's go directly to the example. If you have a code when you expect a pointer to be non-null, and then inside of the function you dereference the pointer.
Yeah.
The optimizer can see that you dereference the pointer, so it can assume that the pointer is not null, and it can remove the check for the precondition. With your implementation, if you just synthesize some code and rely on default behavior, this kind of stuff could happen. And so the check would be removed by the optimizer. Did you do something for that?
The thing is that the check that is going to be removed is not the one from the precondition, but the one from the function body. Is that what you meant?
No, I'm afraid of the function body creating some assumption for the optimizer that will remove the precondition.
No. Preconditions are not assumed backwards. No, it will not happen.
Because by default, the optimizer can do this kind of backward propagation of assumption.
Yeah, but we were concerned with that. But I'm using, for assuming predicates, I'm using the LLVM intrinsic assume. And as far as I know, it will not create that backwards behavior. I tried it, and it does not happen, at least for the examples that I have tried. But we and the C++ committee was pretty much concerned with this. And there is also discussion on this. There is a thread on the, there is an email thread which discusses this. And we are working on it.
So it seems I'm obsessed with loop invariants. So to be able to use this in a static software verifier, right, you typically need preconditions, postconditions, and loop invariants. Does the standard talk about loop invariants at all, or is it not in the standard?
No, it is not in the standard by now. The thing is that I know that many other languages that support contract-based programming support defining invariants, but the C++ committee decided to leave the current specification at a minimum point. So it will evolve along the time in the future. So currently, no, but in the future, maybe for C++ 24, it will be available.
Thank you.
You're welcome.
Yeah, quick question. Would your implementation also work as an extension to C, or is it just in the C++?
No, it's just a C++ thing.
Okay, thanks.
But you are, this is open source. You are free to fork it and to provide C support if you want.
Okay, let's thank the speaker.